Welcome back to Chapter 2, or Section 2, actually. Section 2, we're going to talk about something called permutations. That's some different arrangements of things. Now, we arranged things we were going to eat in a restaurant before. We arranged telephone numbers. Now we're going to talk about permutations, and in the next video we're going to talk about combinations. And the two are similar, but they're calculated differently, so you have to understand the difference between the two, and we'll get to that. So we're going to use that fundamental counting principle again, the one we just learned in Chapter 1, or Section 1, excuse me. And we're going to talk about factorial expressions. Very simple, but we need those to compute how many permutations something has. We'll use that permutations formula, and in class we'll talk about how to use the calculator to get that even quicker. And last of all, we're going to find the number of permutations for duplicate items. Now, the first ones up here that we're talking about where we've got a number of different items, 17 different items maybe, and how can you put those together? Down here, we're talking about maybe 17 items, but maybe some of those items look the same. For example, suppose we're talking about houses, and in a particular subdivision built by the same builder, maybe all the yellow houses look the same. All the red houses look the same. You got 4 yellow houses, 3 red houses, 7 green houses, and the colors within the color, they all look the same. You could walk in one and you wouldn't know which green house you were in. Just another green colored house. Okay, here we go. Permutation. First of all, get the spelling down. This is the important word here. It's an ordered arrangement of those items. Each one of those items is separate from all the rest. No item is used more than once. Each one is a singular choice. The order of arrangement makes a difference. Order. Permutations. Order matters. All right? Now that's going to be different from combination. In combinations, order does not matter. But we're talking about permutations where order matters. So let's show how this works with permutations with a few examples. First of all, let's suppose you got 7 of your favorite books and you'd sort of like to show them off, put them on a bookcase. And maybe you want to make sure that certain books are seen first when you come in the room. For example, maybe you have someone that you know is interested in math. So maybe putting the math book first is important. Or maybe someone is coming that is interested in historical things. So maybe you want the history book to be first, and then another one second, and so on. How many ways can you do that if you have 7 different of your favorite books? Well, use that fundamental counting principle and we can solve it. You can choose any of the 7 books. So imagine putting those books on the shelf, and imagine someone's coming in the room. Here's the door. I'll do my best on this one. There's a door. I would prefer the door, but someone comes in the door and they're walking toward the bookcase. This book they see first. Well, how many books could be in that first position? 7 different books could be there because you've got 7 books to choose from. However, once you've chosen that book, it's in the first position. End of that story. For the second position, how many books are left? Well, you've had 7 books, you've just placed one, there's 6 more books. So now you can choose from one of 6 books. Those 2 books are gone. We want to pick another book. How many books can we choose from now? 5. And continuing, 4 for the next one, 3 choices for the next one, 2 choices for the next one. And once we've chosen those 6 books, there's only 1 book left. So there's only one way to pick the last book. This is how you calculate how many ways you could put those 7 books on the bookshelf, assuming all those books are different. You don't have 7 calculus books written by the same author in the same year. No, they're all different. And you might be surprised that just with 7 books, 5,040 ways you could actually put those on the bookcase. It still surprises me. I don't know about you. Now, if we look back here for a second, notice that in this line right in the middle, you have 7 times 6 times 5 times 4 times 3 times 2 times 1. A nice order to that, isn't there? Well, it turns out that this is a special mathematical model. You start with number 1, next number, going up the integers, and multiply them all together until you have as many as you want. So 1 times 2, 3, 4, 5, 6, and 7. And that is called factorial. We've got a special notation for that. This 7 times 6 times 5 times 4 times 3 times 2 times 1 is called 7 factorial. And we've got a special way to write it. 7 with an exclamation point after it. The exclamation point means we've got a factorial that we're going to calculate. That means we're going to start with 7, then the next one down until we end up with a 1 here at the end. And we'll multiply all those factors together. Factorial because we're multiplying them together, and the exclamation point tells us that we're going to use factorial multiplication. So there's how it looks in general. You start with this number at the top and get smaller and smaller and smaller until you work down to n, and multiply all those together. Multiply all those together. Now we've got something a little bit strange here, but even though you don't see a 0 up here, sometimes 0 factorial shows its head. For reasons I won't bother with right here, we say that 0 factorial equals 1. Now that might seem a bit strange, because if you look at this definition over here, 1 factorial would be equal to 1. So you wouldn't expect 0 factorial to equal 1. You might expect it to be 0. This is a special case. If you're interested, ask in class and I'll show you why. It's easier to show you on the board. So, how do we use that factorial notation? First of all, if you think just a little bit that math is fun, sometimes it's a little bit interesting to do it without your calculator, without using your calculator, because factorial is really fundamental, a fundamental kind of multiplication. Here's how you can do this without using your calculator. Now, this first example could be written a little bit differently. Now, first of all, let's take this. Let's start again here. 8 factorial over 5 factorial. Now, what does this look like? Factorial means You start with that number and multiply it times the next number down, the next, and the next, and the next, until you get to 1. So this 8 times 7 times 6, 5, 4, 3, 2, and there's a 1. That's 8 factorial. On the bottom, what do we have? We have got 5 factorial. And I'm going to start it over here. 5 times 4 times 3 times 2 times 1. Now I'm going to rewrite this, although we wouldn't need to. But notice the 5's cancel, the 4's cancels, the 3's, the 2's, and the 1's. That's why it's written like this. Because if you take the last 5 on the top, that's the same thing as 5 factorial. And on the bottom, this is 5 factorial. So if you write it as you see up here, 8 times 7 times 6 times, and then 5 factorial, so shortening those last 5 digits, and have 5 factorial down here. Those cancel out, and you can manually, in your head, well, almost, you can multiply the 8 times 7 times 6, and you can get the result of 8 factorial over 5 factorial. Now, because of what's coming up, I'm going to erase those. If you want to look at it for a second, go ahead and hit pause. I'm going to clear that for the time being. There we go. Now, look at the second one, 26 factorial. And if you give that a second thought, you think, oh my gosh, I hope I never have to do that. 26 times 25 times 24 times 23, all the way down until you get to 1. That would be awful. That would be really terrible. On the bottom, we've got 21 factorial. However, if we do as we did with the first one up here, part A, when you start listing the factors of 26 factorial, when you get down to 22, you can just finish it off by saying, instead of saying 21, 20, 19, and so on, just make it 21 factorial. And there's your 26 factorial, sort of in shortened form. The reason we stop there, of course, is because you put an eyeball down here, and you see the 21 factorial. And looking ahead, you know that this will cancel with that. They'll both become 1's, and what do we have? A much smaller number. And this is where, of course, even the best of us at arithmetic are probably going to resort to using calculator. So 26 factorial over 21 factorial is over 7.8 million. Okay, now there's a formula for the permutations. Now, first of all, you have to realize you're going to take R items from N items. And you might be saying, this is a little bit too vague for me. I don't really understand what's going on. So let's go back to the first example. Remember those books that you're going to put on your mantle? Well, let's suppose you've got more than 7 books. Let's suppose you've got 20 books. But one of your favorite persons is going to drop by. Maybe your favorite author. That would be cool, right? But you only have room for 7 books. Oops. You only have room for 7 books. And you're wondering, wonder how many ways I could put those 7 books on the mantle if I've got 20 to choose from. Well, that's where you use the formula for permutations. There is the formula, and you're saying to yourself, I don't understand what that means. Well, remember, N represents how many you have to choose from. R represents how many you're actually selecting. So, in this case, we're selecting from 20 books. That goes on the top. So I have 20 factorial. That's 20 times 19 times 18 times 17, all the way down to 1. On the bottom, don't let this trick you. Before you take the factorial, you have to go n minus r. You don't take n factorial minus r factorial. No. Got that? You subtract them first. So how many do you have to choose from? You have 20 books to choose from, but you're only choosing 7. So 20 minus 7, finish that, then take the factorial of that. So what you've got is 20 factorial over 13 factorial. Now, if you were paying attention a little bit ago, you'll notice that this would be 20 times 19 times 18, all the way down to 14, because the 13 factorials will cancel on the top and the bottom. So here's an example of how we could do this. Okay, you and 19 of your friends. So it's 20 people. You decided to start a business. You need 3 officers. You need a CEO, that's 1. You need an operating manager, that's number 2. And you need a treasurer. You got 3. And you got to fill those offices. This is a permutation because not everyone can be a CEO. Not everyone can be an operations manager. And not everyone can be a treasurer. It makes a difference which person is which. How many ways could you fill those 3 slots? Well, this is a permutation because it does matter who is the CEO, who is the operating manager, and who is the treasurer. So we're choosing from 20 people. We're choosing 3 out of those 20. Now what's the formula? It's n factorial over the factorial of n minus r. So what do we have? On the top, we have 20 factorial. On the bottom, we don't have 20 factorial. We take the 20 minus 3 first, then take the factorial. So we've got 20 factorial over 17 factorial. Now remember, this 20 is 20 times 19 times 18, all the way down to 1. But once you get down here to 17 factorial, you can cancel all those out. So you can, if you want to, fill this all out. You'll end up with 20, 19, 18, and all the rest are canceled by the 17 factorial in the denominator. Multiply those 3 together, and that'll tell you how many ways you can fill those 3 positions. You're selecting 3 from a group of 20. Order matters. That's why you're using permutations. This is how it goes in the calculator, by the way. And I can show you how to find that. We'll do that in class. That way I can see individual calculators. I can't see from here. 20 on the top, 20 minus 3. Finish that, then put a factorial with it. There's our 20, 19, 18 that are left after these 17 factorials get canceled. 20 people, and you're just choosing 3, and there's almost 7,000 ways to choose those 3 officers. Now, what if some of them are duplicates? That's interesting. Now, let's figure that we're creating a subdivision. We've got a subdivision, and we've got a street that we're going to fill with houses. And you've already decided that you're going to use 7 green houses. You're going to have 10 red houses, and you're going to have 4 yellow houses. Apparently you've done some research into what people are buying, and that seems the ratio that's going to make sense for you to make those 21 houses. So how many ways can you put them in this street? One side of the street, we're going to keep it simple. Because this first one, here's house number 1, house number 2, and so on. If we're going to have 7 green, 10 red, and 4 yellow houses, how many ways can we put them on that side of the block? Well, that's what we're talking about with duplicate items, because all those green houses are the same. All the red houses look the same, and all the yellow houses look the same. Here's the formula you need. On the top, now make a note up here. All told, you got 21 houses. So that goes on top, 21 factorial. Now I've got 7 green houses, so we'd have 7 factorial down here, times 10 red houses, 10 factorial, times 4 yellow houses, 4 factorial, and that will give you the number of ways you can put those 21 houses on that street. So let's look at an old example, but it works the same way. Imagine the M is one kind of a house, I's are another kind of a house, S's are another kind of a house, and so on. How many ways could we arrange those letters? Well, let's see. How many letters do we have? And how many different kinds? We've got 11 letters in Mississippi. We've got 4 I's. We've got 4 S's, 2 P's, and let's see, did I miss something? 4 I's, 4 S's, 2 P's, and we've got the 1 M. It doesn't say anything about the 1 M. 1 M. So here's the formula. The total on the top, we've got 11. On the bottom, 4 factorial. Those are the I's perhaps. 4 factorial for the S's. 2 factorial for the P's. And although we don't need it much, but there to complete it are times 1 factorial for the M. 34,650 ways of taking the letters in Mississippi and juggling them around and getting something different. 34,000 ways. All right, we've talked about permutations. Remember, as I said at the beginning, we use permutations when order makes a difference. Combinations will be different. We'll get to that next. In the meantime, you take care, and I'll see you next time. Bye-bye.